All right, hello everyone, and thank you for joining us today for this week's session of the Parks Weekly Webinar Series. My name is Amy Price, and I'm the Outreach Coordinator here at Parks College. I'm joined today virtually by Dr. Amanda Cox, who will be showing us around SLU's Water Institute. We are very excited to have you join us from wherever you might be. Thank you for taking the time to virtually visit us and learn more about the civil engineering program at St. Louis University. In total, Parks College has programs available in aerospace, biomedical, civil, computer, electrical, and mechanical engineering, as well as flight science and aviation management and physics. We hope that you'll hear or see something today that piques your interest. Before we start, I wanted to give you an idea of how the webinar will flow. So in just a moment, I will introduce Dr. Cox, who will show you around her lab space and talk about her work. She'll then introduce current student Joey Sieb, who will share his perspective of being an engineering student with you. Throughout the webinar, we do encourage you to submit any questions you might have to the Q&A feature at the bottom of your screen if you are watching through Zoom, or in the comments section if you're viewing through Facebook Live. And we'll do our best to answer as many questions as possible during the last few minutes of our session. Throughout this webinar, you don't need to worry about turning off your microphone or your camera. You can hear and see our presenters throughout the webinar, but we cannot hear or see you. Finally, if you have any technical difficulties during the webinar, please send an email to parksevents@slu.edu and we'll help to address any issues that may arise. This session will be recorded and posted to our YouTube page in the next day or two, and you'll receive an email with that link when it becomes available. So now with all of that information out of the way, I am very happy to introduce SLU's Water Institute and Dr. Amanda Cox. So Dr. Cox, I will hand it over to you now.
Thanks, Amy. Good afternoon. As Amy mentioned, my name is Dr. Amanda Cox. I'm an associate professor of civil engineering at St. Louis University, and my area of expertise is in water resources engineering. This includes design and analysis of systems that have flowing water. You can think of rivers or urban stormwater drainage, or water distribution systems, just to name a few of the different fields that are involved in water resources engineering. But in addition to my role as an associate professor, I'm also the director of the Water Institute at St. Louis University. Today, I'm going to be giving you a tour of our new research labs located at the new Interdisciplinary Science and Engineering building here on our campus. But before I start the tour, I'm going to give you some background information on the Institute. So the Water Institute is focused on innovative interdisciplinary research to support our regional and global communities and their most vulnerable populations. The word water in our name is an acronym. It stands for water access, technology, environment, and resources. The Institute focuses on many critical and persistent water-related issues, such as access to clean water, reducing the impacts of water-related natural disasters, and protecting aquatic ecosystems. We found that these complex issues require a collaborative approach with experts in many fields, such as science and engineering, policy and economics, and public health and social justice. The Water Institute at SLU brings together faculty across several fields within the university, really to help address some of the world's most challenging water-related issues, such as water inequity and water quality. The strength of the Water Institute is that it brings together our unique location at the confluence of the Mississippi and Missouri River, and our exceptional faculty working in several water-related fields. And then finally, it brings together our university's mission of serving others. And the combination of these elements allows the Water Institute to have a unique focus on interdisciplinary research and on integrating social justice considerations into water-related advancements. Some example projects that we have include one that we'll learn about a little bit more today is focused on testing water treatment technologies for use in developing nations to see which are the most effective at the household level. Another project we have is looking at the origin and amount of microplastics that are flowing into our groundwater and local river systems. And then a third project is using machine learning to estimate the volume of water storage available in reservoirs, such as lakes, throughout the United States. And Joey's going to be telling you a little bit more about that project because that's one he's been working on later. So the Water Institute at St. Louis University directly benefits our undergraduate students in a lot of different ways. Probably a key area is that we have opportunities for undergraduate research. Currently, the Water Institute has more than 30 students assisting with our research and outreach efforts. And these are both undergraduate students. Those are students that are working on their Bachelor's of Science or Bachelor's of Arts degree, and then graduate students who have a BS or a BA and they're working on their master's or PhD degrees. We also provide several interdisciplinary curricular options. So for example, we have about 75 different water-related courses across the university in many disciplines. And so these are in areas like earth and atmospheric science, environmental engineering, civil engineering, geographic information science, public health, law, sociology, and we even have a class in theology. And I didn't list all of them, but I think those are the ones I wanted to highlight here. So we just have a wealth of courses for students to study water-related issues in interdisciplinary context. Now let's start our tour of our brand new research labs. We just moved into these labs at the end of the summer. We have over 3,600 square feet of new space in the building. And this includes 3 research labs, a graduate student office space, and shared meeting and workspace for faculty and staff. Our tour today will include the research labs and the graduate student office space. So give me 1 second while I switch devices for our tour. Okay, hopefully everyone can hear me. Amy, is the volume good?
Yeah, you sound good. Thanks.
Excellent, thank you. We're gonna start our tour with Dr. Craig Adams, who's one of our key investigators in the Water Institute. Dr. Adams, do you wanna give us an overview of the labs here, your instruments, and some of your projects?
You bet. Thank you very much, Dr. Cox. So welcome today, and I'm glad you're getting a tour of our new labs here. We love them very much. So I'm a professor in environmental engineering, and so I'm focused mostly on water quality, water treatment, and things along that nature. Dr. Cox's work, as she just went through, is focused on water quantity and how it flows and hydraulics and all these sorts of things. My work is focused on measuring the contaminants in the water and how to remove them and so on. So this work here is going on. So we have projects going on in Belize and projects in Kenya right now, of course, with COVID, nobody's traveling right now. But we work on helping people with water filtration and water treatment to provide clean water to their communities. We have a student here, Crystal Gale, working with several undergraduate students. And what we're focused on here is looking at treatment of different filters and how well they work, how long they'll last, and so on. So what we have, let me start down at this end. This is a community filter. It's made by Life Straw. It's a very, very effective filter, and it will remove bacteria, viruses, and so on. So we put the water in the top of this filter, and over hours, it filters through, goes through a membrane filter, and comes out clean, bacterially clean. We want to see how long will it last, how clean is the water, will it foul, and so on. So this is one filter that we're testing. The next filter is, it can be purchased on Amazon and so on. It's a Sawyer filter. We see a lot of these installed in different countries around the world, and but sometimes any of these filters can, they all have a limited life. And so we're doing 2 in parallel here, because you always want to run duplicates of any type of an experiment to see that it's reproducible. And we're measuring bacteria breaking through in the forms of coliform. We'll show you how we measure coliforms in a minute. This is another type of Sawyer filter that has a smaller pore size. And this is a Life Straw family filter. What's inside the and it is just another type. And you can buy this Again, on the web, everything you buy on the web, this would be a pre-filter. It goes into a feed reservoir and trickles through. So she's testing these filters, and so that's what's going on here. So let me show you some of the other types of facilities we have here. This hood is where we do oxidation. So we can look at a treatment of, we're looking at treatment of compounds in water that cause taste and odor issues, and some of them are very novel. I have a PhD student, Sesha, and she's developed analytical methods to measure 18 new contaminants, taste and odor compounds. And so we're looking at how to treat these best. And one of the things we look at is treatment with ozone, chlorine, chlorine dioxide, permanganate. This is an ozone generator. What we take is we take oxygen in this green bottle down here. Show that. So that's just a bottle of oxygen. Goes up and we convert oxygen, O2 to O3, and then, which is ozone, we bubble it into this water and we get a solution of ozone. And so what we'll do then is we will add little doses of ozone to these taste and odor compounds and look at their treatability. Another PhD student, Summer Malif, is looking at oxidizing blue-green algae toxins. You've heard of blue-green algae in lakes and these sorts of things. Well, they cause a problem for water treatment facilities. And so we're looking at some of those newer toxins that haven't been studied so much, like saxitoxin, nodularian, and so on. But we also look at permanganate, chlorine, chlorine dioxide, and so on in here. This is another hood. So this instrument is, we use a lot of different analytical methods. And if you like chemistry, you might like environmental engineering. And because we get to do a lot of chemistry. Most of our chemistry is aqueous chemistry. So this instrument is used, it's just a spectrophotometer, and it'll measure the absorbance, ABS is absorbance, at different wavelengths and so on. But we also use it to do chemical analyses. So for example, yesterday we were measuring ozone using this instrument. And if you can see one of these, come on over here, Dr. Cox, you can see this is dark blue and this is light blue. So what we did is we put water in here that had no ozone in it, and so it's dark blue. But when it has ozone in it, it bleaches out that indigo. And the difference in this color, we can use this spectrophotometer here to determine exactly how many milligrams per liter of ozone we have. So we can measure iron, we can measure manganese, nitrate, nitrite, chlorine, monochlorine, all sorts of chemicals we can measure with this instrument. We also have a smaller version I meant to bring over, but it's in our other lab. That's about this big that does the same thing, but just not as sensitively and not as accurately, but that's the one we can take to the field. Then you're probably familiar with pH meters. Here's a pH meter that we use. It's fairly high end. It's several $1,000s actually. And it will measure not only pH, which is how acidic or basic is water, but it will also measure, we can buy different probes that will measure things like ammonia. So we can measure by using a probe how much ammonia or ammonium is in the water. It'll also measure whether water is generally oxidizing or whether it's reducing. So it's quite a powerful little unit. So with that, we can go into our other lab and I'll show you a few more instruments. So this is our new instrumentation room. Most of the instruments, as you will see, have not been moved in, but there's a whole suite of instruments that are coming in. One of the first that we brought in is called an HPLC. An HPLC is a high pressure liquid chromatograph, and it's used for measuring various sorts of chemicals like pesticides, atrazine, and so on, a whole suite of chemicals in water, whether it's a natural water or whether it's a drinking water. So the way it works roughly is it has some pumps down here, and it takes these solvents that are on top, be like methanol in water or acetonitrile in water, pumps it up to high pressure, and then we have our samples in here. So we have some sort of a chemical. This one is, well, that's a blank right there. And so then it draws some of that chemical up out of the vial and injects it into that liquid flow stream. Then that flow stream comes over here and it flows in. So say I have 5 different chemicals I want to measure in there. They all come and hit this column at the same time, but the chemicals take a different amount of time to go through the column, so they come off one at a time. And then after that, with an HPLC, these chemicals hit some sort of a detector, some way to measure what's in it. This one has what's called a UV or ultraviolet detector, and it's in this photocell right in here. You can see UV lamp right there. And so whenever it goes by, the amount of UV that is taken out is equal to or proportional to the amount of chemical that's there. So we stabilize this. And then there's a lot of other types of detectors that we can use, like what are called triple quad detectors or fluorescence detector, which we're getting one of those, or other types of detectors. But this is generally what chromatography is like. There's also what are called gas chromatographs. This is a liquid chromatograph. Works in roughly the same way, but you have air flowing through it or helium or some other carrier gas. So anyway, that's our HPLC. Moving on, this is a amperometric titrator, so it can measure whether something is in an oxidizing environment or reducing environment. It does it in a special way. It's sort of a specialized instrument to look at different oxidants in a solution that are difficult to measure by other means. In this area here is where we measure, we were talking about those filters there and other applications. We're interested in measuring coliform bacteria and E. coli bacteria. And so the way we generally do those are with what are called Petri films. You've heard of Petri dishes. Well, these are Petri films. And these have already been measured here. And if you can see this, we see a lot of dots there, blue dots and pink dots. And some have, won't be able to tell, but some have gas around them and some don't have gas around them. The ones with gas around them are coliform bacteria. And the blue dots are E. coli, and the red dots are, well, the red and blue added together are the total coliform. So this is the water from a pond that we're using for testing with the filter. And this is what's treated. This came out of that family filter, the last filter that I showed you. So you don't see any dots there. You see the filter is working very effectively. And so we're studying this at this point. This is an incubator. We hold it at a specific temperature so that these bacteria can grow on this. The pink is called an auger, which is food for bacteria to allow them to grow. Then we use this hood to prevent contamination. And this is where the students will prepare their Petri films. So moving on, if we want to simulate in water treatment plants, we add a lot of different types of chemicals like powdered activated carbon or alum or ferric chloride and other things, chlorine. And we may have to figure out what dosage do we want. We may be able to calculate roughly what we need, but we need to tailor that and get it just right. What we use are these 6-gang stirrers. There's another one back here. We put them side by side. And what you would do is put water, the same water, in all of the beakers. And then you would add different doses of say, alum to it. And then you would see what was the effectiveness for removing turbidity or removing particles. Or maybe we had activated carbon. You know, in your Brita filter at home, you have activated carbon like GAC or charcoal, different terms people use. Well, we use a powdered form in a water treatment plant. So I could add a low and a medium and a high dose. And then I could use that HPLC to figure out how much of the atrazine or whatever chemical we took out. Anyway, that's what we do with these 6-gang stirrers. We simulate water treatment plant operations. So in environmental engineering, you need to measure things at very, very low weights, like tenths of a milligram or even hundreds of a milligram. So this is a microbalance. It's basically it's a scale, like your bathroom scale, but it can measure tenths of a milligram of different types of chemicals. And we have, of course, all our chemicals and all that sort of thing. So another instrument or another parameter that we're very interested in is the cloudiness of the water. Why is that? Because if your water is still cloudy, like here would be a very cloudy water, right? And you can kind of see all that in there. This is a standard. This one has the cloudiness is 600 NTU, nephthalrometric turbidity units. If you can spell that, I can't. This one has, this one is our 20 NTU. So you see it's pretty clear. You can't really tell, but there's a little bit of cloudiness with it. This other one is 10 NTU, and it's even much clearer. Well, drinking water, we want less than 1 NTU. We want it really about 1/10 of an NTU. So we want to get it very low. And the reason is if you have cloudiness, well, maybe bacteria are in there, and maybe bacteria are riding on our turbidity particles. So if you have that turbidity very, very low coming out of a drinking water treatment plant, then you know you don't have particles, and hopefully you don't have the bacteria riding with it. So we measure turbidity in the lab with this turbidometer. It's a Hawk TU 5200, very, very nice turbidometer. And get rid of that, there we go. And so we can read a sample and so on. And so what we do is we take a sample and we put it in the turbidometer, close the lid, and it's stabilizing now, and it's reading and reading and reading. And what it's going to do is tell us the turbidity, and it's stored the data, is 21.2 in that sample. So this device, this turbidometer, is so sensitive that you can take pure water and it will show you that pure water even has a little bit of turbidity, a little bit of cloudiness. It's very low. In the field, we can't take a unit like this, so we take handheld units like that. We put our samples in here and then measure turbidity in the same way. It's just that it's not as accurate. So anyway, in environmental engineering, we do a lot of chemistry. It's mostly water chemistry, which I love. It's really fun. We get to use a lot of different types of instruments, and these are some of them.
Well, thank you, Dr. Adams.
I've asked for questions, but it doesn't really work.
No, we're going to finish up with a lab tour here. There's just one more lab to show you, and I also wanted to show them the cold room, the cold storage room. Thank you very much. So this space here in the instrumentation room also has a cold storage unit, so a very large refrigerator sort of freezer. It's right now it's 3.9 degrees Celsius. So you can see we have some water samples in here. This allows us to keep the samples in a very controlled environment. I believe those samples are Dr. Hasenmüller's. She's a geochemist. She also has works in both of these labs and uses a lot of sophisticated instrumentation. One of the unique things that she looks at is the isotopes that are in the isotopes that are in the water, and she's able to, by looking at the isotopes, to determine, say you have a flood event, what percentage of that water is coming from groundwater versus the actual rainfall. Okay, this space here is our new graduate student office space. Now you'll see there aren't any students in here right now. Periodically we'll have maybe 1 or 2, but that's mostly because of the COVID situation right now that we don't have students in here. We really encourage them to work from home if possible. So we're just walking back to the last lab in our new set of labs, which is the hydraulics lab. And that's the one that I do most of my work in. I focus most on the movement of water. So how fast the water is moving, the forces that the water exerts on its environment, its surroundings. This is what we call a stream table or a flume. We have a reservoir of water at the upstream end and also a reservoir at the downstream end that are connected, and a pump system that's continually pumping water through our table here. So this is our pump apparatus. The pump is actually located in the bottom left there. And lots of different valves and the ways that we can configure this. So this stream table here can be used to study river processes. And a key component of river processes is sediment transport processes. And what we mean by sediment transport are rivers are continually transporting sediment in terms of sands or gravels or silts or clays, and it's sort of a living system. And you can see I've been running this flume for just a few hours now, but I don't know if you guys can still hear me. Amy, can you still hear me?
Yeah, we can hear you. It looks like your video cut out.
All right, 1 second. Let me see if I can get that to come back. Okay, I think I'm back.
Yeah.
Yeah, sorry about that. Must have touched something on my screen here. Anyway, sediment transport processes are critical in how rivers behave. The size and the shape of the river is all determined based on the amount of water that it's moving and the sort of energy in the water, and the boundary of the river itself, which is made up of particles. Those can be sands, gravels, or other types of soil materials. But the force exerted by the water really is the driving factor for the shape of the channel. So we can use this type of model to study particle movement. And one of our recent projects used a technology called particle image velocimetry. And it's a computer processing technology that uses video image from a channel. So for example, here, what you're seeing right now, where you can see the particles moving, we can take these frames from this video and feed that into a computer algorithm that will tell us the velocity of the particles, the distribution of the different velocities that you're seeing in the frame. It does that by following groups of particles, and it's all done, like I said, digitally. It's kind of a novel application, but it allows us to understand how fast the particles are moving, and then we can relate that to the force that the water is exerting on it. It helps us understand the behavior of the sediment transport even better. But yeah, here's kind of the water part of our tour today. We finally get to see some water. So that's going to wrap up the lab tour. So at this time, I'll introduce Joey Seed, the undergraduate student that's working with us. He's a research assistant for the Water Institute, and I'll let him talk a little bit about his experiences and some of the work that he's doing.
Hey everyone, my name is Joey Seid. As Dr. Cox said, I'm a senior student here at SLU studying civil engineering. So just a little bit about myself. So I'm originally from the St. Louis area, and what really brought me to SLU's engineering program initially was three things really. So first was having smaller class sizes, where I really don't just feel like I'm a number lost in a class. Secondly, kind of going off of that, is really just getting that hands-on learning experience. And then third, just being a Jesuit school, there's a really large focus on service and social justice, which I really admire. So just to touch upon these a little bit more. So by having smaller class sizes, it's a lot easier to have closer relationships with your professors. And I really think through that, it's much easier to discover what your true passions are within your field of study. So kind of going off that, like I mentioned, I think that having smaller class sizes definitely allows students to have more hands-on learning opportunities. And I can just tell you from firsthand experience that SLU has a lot of really nice, really high-tech labs that absolutely help me understand the material in my different classes. And third and finally, like I mentioned, just being a Jesuit school, SLU puts a really large emphasis on social justice and striving to really work for that in our everyday mission. So currently I'm helping Dr. Cox work on multiple different engineering or research projects. I find all these really, really cool. But one I find especially interesting is I'm helping her determine sedimentation rates in different lakes and reservoirs across the entire country. And what I really like about this, so obviously this is going to be put to future good use, the knowledge we get out of this model. But probably more than anything else, it's what I really noticed in this project is a lot of the knowledge that I learned through each of my classes, I can really see it applied in these type of real world type projects. And that's something that really makes me value my SLU education a lot and makes me really proud to be a Billiken. Thanks.
Thanks so much, Joey. And Dr. Cox, thank you so much for that phenomenal lab tour. We're so excited about the Water Institute and all of the spaces and all the research that is currently being done and will continue to be done there. You know, it just personally, it's just inspiring because there's so many social and environmental justice implications that are coming out of the work of the Water Institute. So we just have a couple minutes. If anybody has any quick questions they would like to ask, please submit those. But Dr. Cox, I was hoping you could maybe talk a little bit more about the cross-discipline work that's going on at the Institute. And so we're specifically highlighting today civil engineering, and Joey is a civil engineering student, but who else is using these spaces?
Yeah, so like I said, Dr. Hasenmuller she's from Earth and Atmospheric Sciences. So she's a geochemist. So she's not an engineer, but a scientist. And I'm collaborating with her on a project right now that puts together looking at nutrients, or would be considered contaminants like nitrogen and phosphorus, and how those are being transported by sediments. So it takes her expertise in nutrients and couples that with my expertise in sediment transport to look at how sediments and these nutrients can attach to sediments and how they move around in river systems based on the sediment processes. So that's one example. Another example is the project that I described that used the video image processing. That's a collaborative project with Dr. Mitchell from electrical engineering. So when we start to look at some of these more complex computer processing methods, you know, it was apparent to collaborate with him to be able to get that to work really well. He's also been very instrumental in helping with some of our computational fluid dynamics modeling. So it's a three-dimensional modeling, and it's a very, like I said, computationally intensive. So you have to work on several nodes and machines. And so there's a couple examples of how we're working interdisciplinary.
Fantastic, thank you. Yeah, lots of opportunity to get involved, which I think is awesome and very exciting. Final question, maybe for Dr. Cox, but then Joey, if you have something to add, but for undergraduate students who want to get involved in the research that's going on at the Water Institute, what are well, one, how soon are they able to get involved in their undergrad career, and what are some steps that they should take to get a position there?
Yeah, that's a good question. So there's really no limit in terms of what stage you have to be in your education here. So most of my students have been juniors or seniors. And so a lot of times, students reach out to us and just say they're interested in the project, and then we talk to them about that. And then when we have opportunities come available, we'll connect with them and see if they're interested in helping out with that project. So, and this goes with a lot of different things in life, just reaching out to people and expressing interest. That's the best way to kind of get your foot in the door. And then when opportunities become available, that, you know, we know their names, we know they're interested and they're passionate about it. And so that's a really strong way to go about trying to get undergraduate research opportunity.
Excellent. Yeah. Joey, do you have anything to add? Was there anything, you know, specific that you did to get involved?
Yeah, so I completely agree with Dr. Cox. And, you know, I really think a big thing is just kind of understanding your passions and just putting in a lot of hard work in your classes to really know what you want to do and really what you're passionate about. And that's what I really like about SLU is just having those smaller classes and being able to build up those relationships with your professors.
Excellent. Well, thank you both so very much. Please pass along our thanks to Dr. Adams as well for showing us around today. And thanks for anyone who joined along today and was viewing our lab tour at the Water Institute. So we hope that you did enjoy that visit. And if you would like to learn more about the engineering programs at SLU, we encourage you to visit slu.edu/parks. In the post-event email that we send out, we'll also include a link to a webpage all about the Water Institute, as well as a few of their social media handles, so you can follow along and see what exciting work is coming out of the Institute right now and in the future. So as always, please reach out to us at parksevents@slu.edu if you would like to connect further. And finally, please plan to join us for our last webinar of this semester, which will be next week on Wednesday, November 18th at 12 p.m. We're going to take a visit to the Chrome Lab at Parks College, which is also very multidisciplinary of all of our engineering programs. So thanks once more for joining us, and have a great week and weekend ahead.